Looks like we've got a good amount of people in here. I'm sure more people will join. The meeting's open, so people can hop in as they go. But yeah, I'll go ahead and get started. So, hello, thank you everyone for being here. For those of you who don't know, this is the first part of a four-part series called GIS and AI that the California Geographic Information Association is hosting. This will be session one, how GIS and AI work, and integrating GIS and AI technologies. We have two great speakers here today, Dr. Kostas Alexandridis and Dr. Soheil Sabri. And I'll introduce them soon, but they'll be presenting today on this topic, and we'll have an opportunity to open up a panel and discuss. So, talking about upcoming events, there's a QR code if you haven't registered or you just shared this link. On April 24th, we'll be having a session at the same time on Friday on GIS and AI, AI skills in the workplace, training and learning. On the 29th of May, we'll have a session on AI policy, legislative and management aspects. And on June 26th, we'll have a session on AI ethics, sustainability, and equity in social and collective settings. So yeah, more of these to come. I think it's the last Friday of every month from 12 to 1:30. For those of you who don't know, we have other things that we do here at CGIA. One of those is the exciting awards program. So if you haven't already, nominations are open through May 8th. So if you'd like to nominate someone for excellence in innovation, coordination and collaboration, mapping and visualization, a student of potential uh, that excels, excellence in teaching, and of course the chair's award categories. You may nominate them using the QR link or the link below. Um, for those of you that are attending the Esri UC or who might be in the area, we'll have a awards ceremony at Revel Revel on Monday, July 13th. More details will come out, but we'll be passing out awards to the winners of those categories then. So, just a little pitch before we get started. The California Geographic Information Association is an association that's focused on bringing the GIS community in California together. Um, we would love for you to join and become a part of our organization. There's several great things that we do to involve the community and to bring people together. One of those is to advocate for the GIS community as a whole uh, and bring our issues to the state and federal level to make sure that we as professionals have what we need to succeed. We produce information about what we believe the best practices are for GIS in the community and try to share those best practices around. We recently created a information sheet on surveying and GIS, which has been quite helpful, and we've been sharing that out widely. We create peer networks and bring people together in social events. We host Mappy hours. We host tours around the state for people that are members to allow for networking and expansion of your community. And we provide information and share out information on, potential trainings, education, jobs, and events like this, where you can learn more about a topic that you might be interested in. So if you're interested in registering and becoming a member, there's a QR code on the slide and a link below. And after I'm done giving these presentations and introductions, I will drop those links in the chat. Just so you know, this session will be recorded and posted on our YouTube channel. I believe we have already started the recording, so that's going and being transcribed. If you'd like to see this session or you miss another session, just know that you'll be able to go into our YouTube channel and be able to watch it yourself. So without further ado, I'm going to introduce our speakers. Our first speaker today will be Dr. Kostas Alexandridis. He is a GISP, GIS analyst, and spatial complex system scientist with the County of Orange in Orange County, yeah, and is a part of the OC Survey Geospatial Services. He has over 20 years of experience in research and academia and currently serves as the GIS analyst and spatial complex system scientist at the County of Orange and the OC Survey's Geospatial Services in Santa Ana, California. His skills and knowledge include spatial data science, advanced geo AI, machine learning programming, modeling and simulation for digital twins, and GIS science in support of the digital transformation work at the County of Orange. He holds a PhD in natural resource policy from Purdue University and serves as a co-chair of the Academia and Research Working Group at the Digital Twin Consortium, collaborating with leading experts and organizations and developing and advancing digital twin technologies and applications. Previously, Dr. Alexandridis served in multiple faculty, university, and government positions. He is currently serving in the board of directors at the CGIA as an advisory board member for the Big Data Executive Certificate Program at the California State University in East Bay. He's a member of the IEEE and the IEEE Computational Intelligence Society, a member of the IUCN Committee on Ecosystem Management, and as a member of numerous other professional organizations. His mission and vision is to contribute to the scientific and social understanding of complex spatial systems and their implications for natural resource management, policy, and decision making. So thank you, Dr. Alexandridis, for being here. I will share your LinkedIn profile and email, but if you want to reach out to him, that's how you can. And I'll also introduce our other speaker before handing it off. We have Dr. Soheil Sabri, the assistant professor and director of the Urban Digital Twin Lab in the School of Model Simulation and Training at the University of Central Florida. Dr. Sabri is an assistant professor and director of the Urban Digital Twin Lab in the School of Modeling, Simulation, and Training at the University of Central Florida. He holds the titles of urban planner and geospatial scientist with a primary focus on developing urban digital twins, geospatial AI, multidimensional planning support systems, and real-time analytical tools tailored to empower planners and decision makers with evidence-based, data-driven insights for critical infrastructure, autonomous vehicles, built environment, human interactions, and urban health. He contributes to the education, scholarship, and professional training of digital twins, including the Digital Twins Graduate Certification Program at the SMST as the lead editor of a recent book, Digital Twin Fundamentals and Applications, published by Springer Nature. He is the ambassador and co-chair of the Academia and Research Working Group with the Digital Twin Consortium. In addition, he has contributed substantially to the IEEE Digital Twin and Parallel Intelligence Urban Digital Twin Working Group of the Open Geospatial Consortium and the Digital Twin Task Force of the Smart Cities Council in the USA and Australia. He's an honorary senior research fellow at the University of Melbourne, Australia. And we have Dr. Sabri's information up there as well, if you'd like to get in touch with him. So just so you know how this works, we'll have Dr. Alexandridis present first, and then we'll have Dr. Sabri present second. If you have any questions, feel free to post them into the chat. We'll try to, get those down and go through them as we go. But once both have been able to present, we'll open up the floor to questions where Dr. Alexandridis and Dr. Sabri can answer questions that you might have. So let's see. So without further ado, I'll go ahead and stop sharing and pass the floor to you, Kostas, whenever you're ready.
Yes, let me share my screen. And turn on the presentation mode. Okay. Good afternoon, everyone. And thank you, Thomas, for the really delightful introduction. Today, I'm going to provide an overview of some of the methodologies and approaches for integrating GIS and AI technologies. Of course, I understand this is a very, very big topic and it's growing exponentially the last few years. So what I will try to do, provide a kind of theoretical background and then maybe present 2-3 applications that I've been doing on my work. I understand that we'll not be covering all possible topics on Geo AI, but it will give you, I hope, some food for thought and further exploration. This is work that's been done as part of my everyday work in public works, geospatial services, but also it's coming up from different work that I've been doing with the Digital Twin Consortium. I worked with Soheil before, co-authored the book together. So we're working on that integration of geo AI and digital twins and in general the digital transformation technology. And of course, you see that logo on mine scribble, that's my personal kind of professional space. So it's not all the work that I've been doing with my organization, but it's professional work being done on different fora as well. Let me start with something kind of fun. So often, and I think it's more often than not in the
Hostess,
last big year. Hello?
hi. Someone in the chat said your volume's a bit low. Is there any way to turn it up just a tiny bit before you dig in?
Yes.
Thank
Uh,
you.
let me, I have to stop presenting for a second. So let me change my audio. Is that better now?
Yes, thank you.
Okay, good. Sorry. All right. So what I wanted to start with is, we find ourselves, especially when we're looking at the integration between GIS and AI, is we live in a world where uh, we move from simple solutions to very complex. And that involves not only our problem space, where we're facing a lot of complex problems, but, as it is naturally deducted from, is that our solution space has to be as complex as our problems, at least. So we're moving more and more into more complexity space as societies and as the solution space of our problems. So let me start with from the geospatial standpoint, with that, what we call geospatial composability. That complexity increases as we start with the geometric representations of objects in space, to 3D objects, to spatial, all the way to geospatial, which incorporates not only the patterns in space, but also the methods and the explanation and the analytical tools to uh, to derive some solutions or answer some questions or even inform some decision making. And that transformation to the complex geospatial reality, from geometric to 3D to spatial to geospatial, happens in integration with a lot of new technologies, intelligence that comes from GeoAI, in collaboration or in coordination with increasing and standardizing our geospatial inference, which is often required in achieving better performance on our GeoAI methods and classifications. And of course, oftentimes when we start integrating advanced methods like modeling and simulation, we need a robust framework, because we are using, especially with AI, a lot of layers, a lot of different spatial representation. So those two things, the increase in spatial and geospatial complexity, along with those three kind of pillars of methodological approaches in intelligence, interoperability, and robustness, are really, really important when we're looking at geospatial systems. So let me make an attempt to a typology of GeoAI methods. So we have the more traditional, there are older methods that they are big data driven, right? And in line of what I was talking earlier, We can start with locational AI, whose goal is to provide locational intelligence. Often deals with simple point systems, so it attempts to answer the question where something is. Then we have the spatial machine learning methods and pattern recognition systems that try to address not only where things are, but how they're arranged in space, right? And then beyond the machine learning and pattern recognition systems and methodologies, we have developed the last few years a lot more advanced spatial learning and classification systems. So their goal is not only to detect, to do machine learning and detect patterns, but also to develop some kind of classifications, some kind of advanced learning. And that includes deep learning, convolutional neural networks or artificial neural network methods. Those exist, spatially explicit neural networks exist for years, but the advancement of deep learning methods now in collaboration with AI has taken them much more further and proliferated those methods in AI. And of course, on top of that, we started seeing a parallel intelligence that comes from agent-based modeling and distributed artificial intelligence. When you think about distributed systems, think about swarm intelligence. So like a swarm of agents that the whole is more than the sum of the parts. So that intelligence is achieved not just by doing certain tasks, but also from collaboration and communication of engines and goals and policies. So that's one more step further. So we're not only creating systems that learn and classify objects and patterns in space, but also develop, intelligent agents and software, artificial intelligence software that talk to each other, allocate tasks, achieve goals and targets. Right. So this is on the one hand, the big data-driven technologies. Those technologies have started somewhere in the late 90s, but the last few years have been, as I said, proliferated. And that's one side of GeoAI. The other side has to do with large language models that have to do with natural language processing. And the first one is the one we see today everywhere. It's the large language models. They're not necessarily spatial, so whatever intelligence comes from those, it comes from understanding of the meaning of certain words, certain paragraphs, certain documents, etc. Now there is a whole push, and I think in the next few years we're going to see a lot of development in domain spatial intelligence, right? So this is, instead of having massive models you train, once a year, using a lot of resources, we're going to start seeing small, explicit domain LLMs that they're trained on specific systems with a specific expertise. And of course, on top of that, they talk to each other, right? Instead of having one large language model that it's, the entire world, we might have a geospatial one that has expertise, for example, on smart cities and only trains for those. So this is more efficient and more advanced kind of, because it combines LLMs with distributed artificial intelligence and swarm intelligence to achieve results. It's much more cheaper to train those models and those specialized models, instead of try to reinvent the wheel. Its domain learns from the expertise of each other. And of course, you also see the latest push into agentic task-based LLM intelligence that takes the large language models, either agentic, either the general or the domain ones, and adds task-based intelligence, right? So it asks agents to take what it learns from the LLM and do something. And that helps with automating systems, automating processes, coding, programming, etc. And of course, if we now combine the left side with the right side, we started seeing a lot of push on edge AI. That goes with domain intelligence, but instead of having artificial intelligence models you train and you apply after your data came, why not set up our AI systems, pre-train them, set them where our sensors are, and instead of sending all the data over the internet, why don't we just detect the patterns and send only the patterns? This is what we call edge-based intelligence, and that includes small servers that they're set up in locations instead of having some centralized computer analyzing everything, processing on site, and only sending the detection processes. And that is combined, on the other hand, with distributed artificial intelligence and agent-based modeling as well. So that's my attempt, and I'm sure I'm missing things, but this is a rough cut typology of GeoAI methods that we can see right now. Now, when it comes to GIS, the right side, the LLMs and domain LLMs runs into certain type of problems because, well, we can start classifying with natural language processing and language models quite a lot of metadata and description of GIS, but because of certain kind of industrial practices, we cannot classify GIS data completely based on language. For example, Esri geodatabases are, protected product of Esri. If you try to open any geodatabase through Windows, you won't see any layers, you won't see anything else. There's no way Windows and LLMs access the information inside geodatabases or inside maps without running into commercial license issues. So, and I'm sure that Soheil will talk a little bit about standards with OGM, but there might be some efforts, and that's where standardization and interoperability comes in. So let me put the methodology in perspective. Some of the methods like deep learning, machine learning, they are nested systems, right? So if you look at machine learning is part of artificial intelligence and deep learning is part of the machine learning. So some of those methods, they are not independent with each other. They might be nested within each other. So let me go to the realistic, pragmatic aspects with, I'm sure a lot of us in our organizational professional work are facing, right? We are increasingly facing a lot of data challenges, right? We might start observing inflows of too much data, and it will be difficult to make sense of them without having AI or some kind of methods to analyze them. We have data silos, right? I can see it from my organization. You have different departments, different groups. We learned in the past to operate into data silos, which is a problem by itself because now all of our systems and our integrated system requires breaking down those data silos as well. And of course, bottlenecks. Oftentimes we develop or we design system to operate as a single source of data. Today we're starting moving and AI systems and integrated geo AI systems require multiple sources and independent sources in a more loose partnership. So those are some of the challenges we face together on our professional work that we need to change our perspectives and attitudes towards how we address those. For example, this is one of the type of things that we often use on multi-sensor systems in GIS, right? We integrate data coming from global navigation satellite systems, global positioning systems. Often some of those systems are adjusted for their position, not the relative position of the object, but also the position with the Earth. Oftentimes you have to calculate time in orbit, positioning. Oftentimes some of those multi-sensor systems, they are used for very advanced and very sensitive applications. For example, look at conditioning of dams and the engineering prospects, post-earthquake sensors, navigation systems. And today we are started moving on almost on top of the GPS system. We started developing IPS, which are indoor positioning systems as well. And this is an example of some of the work we have been doing in the John Wayne Airport. So what you see in the left part of the image, we have monuments and geodetic control network of positions within the entire airport. And that is tied, what you see on the right side, with a orange or red dust lines. That's a GPS real-time network that tracks not only the positioning of the objects, but also automatically adjusts the positioning of the Earth. Because I hope you know that in California, we're moving about a couple of inches a year. The Earth is moving. So if you have data that there are 10 years off, you might be feet off of the original positioning. So it's really a need to develop systems that automatically readjust your global positioning system and its relationship to static objects. So, and that's where the whole network of real-time positioning does. It ties to those geodetic control and readjust the positioning. And on the row in the left, you can see some of the examples of our engineers and the field crew setting up those networks. And this is in preparation to set up indoor positioning systems, which has to be very accurate and very detailed up to the centimeter or an inch or a fraction of an inch accuracy inside closed doors. If you try to use your cell phone inside an airport or inside a closed space, you'll see that it's not very accurate because concrete and other type of enclosed spaces really affect the accuracy of the GPS system. So we need more accurate systems, and we're moving towards those. Oftentimes, we have to take approaches on data that operate across scales, from the mega to the very big scales to the very detailed scales. So as you see here on the left arrow, we have systems that has to be adaptive as you're moving from the bottom to top, which is the bottom is a very detailed, very locational, all the way to regional and big data systems, right? So cities and regions to the kind of big systems, city blocks and building information models, to asset management for buildings, all the way to objects and smart objects and LiDAR systems for streets that come in preparation of self-driving technologies and all those kind of things. So we have to be able to adjust both the detail and the resolution of our models as we change scales, but also the extension of the scales and the detail of the scales. So designing GeoAI and geospatial systems that have embedded that scalability approach is really important. So this is an example of some work we did a couple of years ago with digital twin for Orange County. This is an example of scalability. So this is about, on the top left, is about 850,000 building footprints in Orange County. As we're going down, we created 3D digital footprints. As you're going into the neighborhood of the area side, here you can start seeing facades of buildings all the way to the network with really detailed representation. And then if you go even more, we have digital scanning, the building information models, 3D buildings, all the way to LiDAR scan interior of buildings and positioning of different objects. So this is all part of one system, which the detail added is changing as you change resolution, right? So, and all is done based on AI. So this is an example of NVIDIA Omniverse application that takes, and each one of those things you see in the map, you see on the right is a digital object representing it. And this is an overview of 850,000 3D buildings in our county. But also, oftentimes we can get from, LiDAR and aerial photograph to digital objects, right? So this is an example. We scan the images through LiDAR, then the AI started detecting certain objects. For example, this is the standard engineered parking lots. Because those are built with US standards, they can be detected, and AI can detect those objects and convert them from aerial imagery to digital objects as well, right? So this is an example of new technologies that comes from the sensors to the LiDAR to the aerial photographs all the way to digital object representation, right? So when we're talking of GeoAI and AI development in GIS, we have to take a data-centric approach, right? So how we aggregate different data that comes from different sensors and different sources. It's really important to validate the data because a lot of times the AI models are as good as the data we provide. We often have to standardize the data to talk to each other and create those data pipelines that allows us to automate those workflows over time. But when we develop intelligent GeoAI applications, we have to consider certain dimensions of intelligence and decide which one to include, right? And this is one attempt to classify those approaches. So, of course, we are talking mainly about the spatial and geospatial intelligence here, but oftentimes our data might have temporal and transient intelligence, right? So it might not just be objects or patterns in space. There are also temporal patterns as well over time, right? There is also predictive analytic intelligence. How intelligent are our systems to predict changes, especially for decision making that we need to make predictions or provide an intelligent analysis. And of course, when you start introducing decision making, you have to deal with human aspects, behaviors, beliefs, attitudes, intentions, and that's where the cognitive behavioral intelligence comes. A lot of our systems, for example, dashboards for 911 or emergency management system, it has to take into account the decision-making attitudes and behavior, right? And of course, visual intelligence, that's where digital twins come. It helps with more 3D and metaverse representation of virtual reality. We're enhancing the perceptual visual intelligence of the end users to be able to improve the decisions rather than giving them a bunch of tables and data. And of course, constructive engineering intelligence, that's where we engineer sensors and sensor systems And of course, the last part is more the reactive and adaptive. How we build systems that instead of being static, they react to changes, the ability of our systems and components to react and adapt to changes dynamically, or use distributed intelligence. I talked a little bit about that earlier. So when we design GeoAI system, we might want to create a mix and decide which type of intelligence we use. And of course, the more constructive and reactive, it's more data-centric. The more cognitive and visual is decision-centric. So we have to kind of balance those approaches. So when we build those systems, we have to build all those dimensions in all the dynamics of our systems, our models, and our processes. On the one hand, on how we measure and assess our intelligent GeoAI systems, what kind of models and how we use them, and what kind of processes of automation we use. And of course, the scalability, how the integrative, so how we move from institutional collective decision making to our cognitive and social dimensions to our technological domains. So let me put a framework of interest. Oftentimes GeoAI allows us to achieve full automation of workflows, achieving real-time results. It helps us move towards a more augmented reality approach to high resolution data. It provides a real-world production experience and implementation of big data structures, often dealing with Teradata workflows. And of course, oftentimes it allows for successful partnering of government and public community benefits with the private commercial sector, such as AI and cloud processing. Of course, for the things that I'm involved more, we are interested in intelligent management and operational processing of critical urban public infrastructure, preparing digital transformation for communities and citizens, provide scientific approach to geospatial provisioning, reduce the uncertainty and subjective interpretation of decision making, and implementing knowledge economies of scale. Of course, such an approach and such of methodologies utilize highly valued skills and competencies, reduce labor costs while producing added value services for citizens, and it adopts an innovation, creative thinking, and cutting-edge technologies approach at public service, and of course promotes learning and teaching and outreach for the next generation of employees and collaborators. In terms of technology trends, I'll give my view of where things are moving. So more likely than not, we are moving towards real-time, real work, and reality-like visualization. We're moving more and more to cross and interdisciplinary approaches. So it's not enough to address the silos I was talking earlier. Oftentimes, as professionals, we have to think, what can we do to stand out from the crowd? How we can, our skills and training set us apart? How we can adopt a continuous learning and skill development attitude because the technology moves in unprecedented, fast or rapid pace, and we need to catch up. We have to learn and work and thrive in group environments because it requires a lot of expertise that is impossible for a single person to have. And we have to learn to embrace that complexity in cutting-edge technology and also think outside the box, right? In terms of big data and open science for GeoAI, there's a technological push towards big data. We need to develop integrated solution with real impact for our societies. And there is a movement in the industry towards open data, open source, and open science, those three dimensions. So how we provide open data available to everybody, open source, so the programming used is open as possible, and open science. You see and proliferation in journals that they're open to the public, etc. So let me move into give you some examples really quickly. I know so this is an example that we did. We did almost 8 million photosphere, like the Google Open Street View. We had our vehicles going out, and every 10 feet, the entire county capture 360 photosphere, and also LiDAR capture a LiDAR of the areas. And then we use a GeoAI method to start recognizing objects. So what you see in the red here, we took a zone which is more in the visible right in front of the sensor. You can see in the bottom the sensor of the vehicle. We cropped it into high resolution, 4,000 by 1,000 pixels. And because it's 360, we know that those 8,000 pixels across, they represent 360 degrees. So we segmented the image in different directions, right? So each direction represented a direction of the vehicle moving, and then we feed it into AI, and we did some adjustments. I won't go into detail into that, but then we tested both Google Cloud Vision, Cognitive Vision, and Azure Cognitive Vision AI in collaboration with a locational detection of AI. We use the deep learning convolutional neural network model. This is like the architecture. It has so many layers here. And then we started looking at different objects like stop signs, fire hydrants, and things like that. So a lot of those detections, this is a detection of a tower, of a car, of a van, etc. So a lot of those detections are, and this is how we traverse the entire county, 10 feet apart. I have a video here of detections. So we tagged all those detections as it moves along, like a stop sign, in almost real time. But then it feeds back into a network. So this is an example of our early pilot study in North Tustin. We start seeing stop signs. We can see the same stop sign up to 80 feet beforehand, and we have a paper that we say it's almost close enough to start detecting for self-driving cars, and feeding this, hitting the stop sign. But the accuracy of those are a fraction of an inch. Another application is dealing with GIA to look at patterns of traffic incidents. This is almost more than close to 15 years of collision data on Orange County, day by day and hour by hour. We started feeding those data and started looking at patterns to start looking how we can improve our road infrastructure to reduce fatal crashes and finding areas where we're having problems, right? So we can started seeing some traffic incidents, and in the bottom one, you can see the cities or the areas where we have higher levels of traffic incidents. So this is another example of using GeoAI from massive data. This is about 500,000 collision incidents that we analyze and feed. We also use real-time data that comes. We have a partnership with Waze. We get the back end. We start using the partnership data along with video and real-time capture of images from traffic cameras from California, from the California Department of Transportation. So we feed all those systems into our AI to start looking patterns. Well, we start looking at patterns of traffic coming for ways and then start counting data from our camera sensors. There's about 750 traffic cameras here in different highway areas. So that's another one. The one work that we did with Digital Twin Consortium, we did GeoAI indoor positioning model for smart airport to start looking at the distribution of passengers on different stages on a smart airport, from the parking structure, the check-in, the security, all the way to the gate for incoming passenger flows to outgoing. And that's an example of agent-based technologies. So this is an agent-based model that actually simulates the flow of the passengers as they move to different areas. And the inside is the airport. Um, the blue ones are the outgoing passenger, the incoming passenger. The green ones that are outgoing. The ones on the left are the gates. As the one with the black is the security. So we start looking at how people pass those and how the distribution, where the bottlenecks, how we can improve the distributional flow of the passengers. So those are some examples of using GeoAI agent-based distributed intelligence to start understanding dynamics of how we can improve the workflows. And of course, this is some of those are taking integrated IoT development. We develop IoT sensors for our compost on our different locations where we take our garbage there. I'm not gonna go through a lot, and this is some example algorithms of big data machine learning that we use that can be used with GeoAI. Of course, the neural networks, there is the average perceptron method, and then support vector machines. There's a more Bayesian probabilistic framework that says, it based on the premise that oftentimes the more information we have, the more likely it is to change our belief about certain things. And that's, you have point machines and naive Bayes and some of those. So for example, some of the decisions you make on medical diagnostic systems are Bayesian systems. Some of the engine, the Google engine that determines which website will give you results when you search in something, that's the same kind of algorithm. And of course, there's regression-based systems, linear, logistic, random forest in increasing complexity, and all of those are spatially explicit, which makes it very complex because oftentimes in top of what affects what or what causes what, we have to figure out how things are arranged in space and what is the effect of what we call spatial autocorrelation, the idea that things that are closer are more likely to be spatially dependent on each other, right? So when you have a source pollution, things that are closer to the pollution are more likely to have higher level of pollution, and so on and so forth. And of course, there's a whole range of algorithms, tree and search-based, decision trees, boosted trees, and principal component analysis-based. So those are all those type of machine learning methods that can be used on different types of machine learning and parsing recognition. And those could be supervised. That means that a human is in the loop and evaluates those, or unsupervised, which means it's all fully automated. And of course, part of the supervised, somewhere in the middle, is what reinforcement learning. Some of the robotics is when you're training the model, if it does a good job, you give them a reinforcement. If it does not, if it creates error, you give them a disincentive. And so the model over time starts learning from its own mistakes. And this is an example of spatially boundary prediction of objects based on a two-layer classifier, very simple. You give a latitude and longitude. You have a two-layer artificial neural network. At the end of the day, it will tell you whether or not that longitude or latitude is part of one object or one group or another group. It's called spatially binary, or maybe it's within, it's more likely to be part of one boundary or another. So I'll stop here. I know we don't have a lot of time, but I think there is quite a lot of, initial presentation of how things may be used. I wanted to kind of piggyback back to my initial thought is that right now we have a lot of geo AI and geospatial technologies that has to do with machine learning, pattern recognition, all those type of data-driven methods. And those are highly developed. Some of them that I saw that you need programming experience to build them, but growingly in the last few years, Esri, for example, has built geoprocessing workflows and objects and menus that does that already, especially with the satellite imagery and the imagery GIS. So you don't need to reinvent they have even pre-trained machine learning tools. You can load them on your Azure software and run them and, do a land use classification, detect, pools or trees or things like that. So there is quite a lot of work being done already. So you don't need to program anything from that side apart from running a geoprocessing script and Azure software. On the other hand, on LLMs, as I said, because of the proprietary software, we need, and I don't know what Esri is doing to on the proprietary side to develop LLMs that detect layer properties and attributes. But we can use LLMs right now on GIS objects, on their metadata, on the descriptions or document aspects, not on the data themselves or their attributes. But there are efforts undergoing here, and I hope to hear more from Soheil to see if there's any effort to standardize those processes with LMS on the Open Geospatial Consortium. But now you saw we have way more applications and processes that I could show in that presentation, but I hope it gives you an idea of the technology aspects of integrating GIS and AI. And I'll stop here, and I hope I can answer your questions later on. Thank you.
Thank you, Dr. Alexandridis. I'll go ahead and pass the floor to you, Dr. Sabri, whenever you're ready.
Thank you very much. Thank you, Kostas. I appreciate your great presentation. So, good afternoon, everyone. It's a pleasure being with you, and thank you for inviting me to this forum. I believe that Kostas laid the foundational aspects, and I'm going to give you a little bit of introduction of what we are doing at the Urban Digital Twin Lab, and set the scene for application of these technologies based on the challenges and complex environments that we are dealing with. And I'm going to explain what do we mean by digital twin, what is the urban digital twin, what is our idea, and what is the role of Geo AI in integration with that, and also some applications and concluding remarks. So, Urban Digital Twin Lab is trying to integrate the technology with the social dimension. So this is a socio-technical aspects, and myself as someone who have done urban planning as a social scientist and also the geospatial science. I spent 10 years in the geomatics department at the University of Melbourne in Australia, and developed and worked with the software developers, geospatial engineers, and so on. The idea is coming from the middle here, as you can see here, model-based, anything that is coming from model-based engineering, and everything we want to do, any intervention in our urban and regional areas for built environment, natural environment, and even social systems, we need to model it. Certainly, this is a very big requirement, and that requirement is really supported by emerging technologies like IoT that is coming up right now, as you could see in Kostas' presentation, and structured and unstructured data like the text, image, and so on. And geospatial artificial intelligence specifically is very important for addressing all those requirements to be able to deliver intelligent urban automation. And along the way, one thing we shouldn't really forget about is this corner of this triangle, the architecture that is really addressing the security, trustworthiness, and sensitivity of the data and the results of analysis. And the other side is about the communication, how we are going to communicate this with the end user. Extended reality, mixed reality, and even the email or message or any type of communication and engagement with the community is very important. So I would like to acknowledge our team is growing. We are very young at the University of Central Florida, but this work normally is not my work. Is normally my colleagues and all the PhD students, postdocs, and graduate, undergraduates, and also. I would like to make sure that I acknowledge my collaborators, like Kostas is one of my great collaborators in the Digital Twin Consortium, and also other collaborators in the industry, government, and academia. So let me put put it this way from the global challenges. All of us, we know that we are dealing with issues related to the global challenges in terms of the fire or hurricanes or flood, earthquake, and so on. Urban heat island is kind of silent challenges that we are developing ourselves because we develop high-rise buildings or central business districts with higher density of buildings in urban areas and some other parts, so that we can make an island of a high temperature area, which will impacting the energy consumption, our sustainability, and so on. And at the same time, issues like the design of the infrastructure that might actually contribute to challenges like accidents, fatal issues that Kostas just demonstrated over 15 years now. And also the disease transmission across different entities in the environment. And there are some cascading issues, like if there is any wildfire that you all were witnessing in California just last year, you will see that the disease is spreading. So those cascading areas are making things complex. So from the complexity perspective, certainly we are dealing with a very complex environment, and the ecosystem of open, harmonized, and interoperable information models and data sets across these different systems is really a lack, is a challenge. So we used to be in paper-based and in two-dimensional. Nowadays, we are moving towards digital and also three-dimensional, but certainly we need to go to 3D plus, because we are dealing with a lot of new real-time data that should be integrated, and those real-time data can be even can be actually improving the level of decision making. The data should not be siloed, should be integrated, standardized. That silo of data will lead to the isolated decision making, and that isolation really leads to the ad hoc type of activities across different departments in the local governments or even state governments. We are dealing with the transportation, environmental, and then the socio-economic developments. If they are integrated, certainly they are not ad hoc, and these will increase the level of trust and the level of certainty across all these different application areas. So certainly these are the requirements that we need to do. So if we are dealing with the data that is underground, how we really address these hidden type of assets underground, how we can bring that up into our models and analysis. And if we want to use renewable energy, for example, how we are going to use all the available data to measure the benefit, the return of investment. So with that, let me go to the digital twin. Apparently, Dr. Michael Greaves, one of our colleagues who started this idea and started from a traditional way of modeling and moving towards the more interactive modeling, and then real time, and then even front running simulation. That means even go above the real time or further than real time to be able to make a decision for any physical entity. So this is what happens in the evolution of the digital twin. But what is the digital twin? In fact, in the book that I myself and Kostas and other colleagues we edited, we have the digital twin, the consortiums of the definition, but this one is very long. Let me draw your attention to this particular case here. So this definition here has got several keywords that I'm going to talk about later on and along the way, and see what is the role of GeoAI into this. So the digital twin is an integrated, data-driven virtual representation of real-world entities and processes. So by data-driven, we are talking about the AI. We are talking about we are not talking about the physics-based like computational fluid dynamic or any sort of models that are computational heavy. We are talking about the data that is fast processing and is trying to address the situations in a very low latency, high frequency situation. So the digital twins major contribution is bidirectional synchronization, meaning that from the physical systems to the digital systems and vice versa. So, and also the frequency and fidelity is very specific. It's not always promised to be very accurate, but is trying to be fit for purpose, depending to the application. In the digital twin environment, certainly we have three components. One is the physical environment, and the second is the virtual environment, and then we have a synchronization between these two. And that synchronization, as you can see here, and this is by national academics and science, engineering, and medicine, they really laid down to the definition and the diagram in a way that is actually this physical counterpart should be connecting, and the circle should be going on in that frequency. So there is no difference of this diagram with the previous concept. So, and also here, as you can see here, verification, validation, uncertainty, quantification, ethics, security are very important to be addressed. These are non-technical aspects. These are but very important, as you could see in the previous presentation. Bayesian systems or any sort of uncertainty, mathematical uncertainty quantification is very important. Now let's move on to the urban digital twin. Now what do we mean by the urban digital twin? So here is our mind map from the urban digital twin, where we put urban digital twin in 3 pillars of data, model, and visualization. So from the data perspective, we always deal with the data which is in text formats, in 2-dimensional or 3-dimensional. As you could see in the previous presentation, we had a lot of images. We have LiDAR data, IoT, or even video feeds. This is the data part, and then the model part is trying to make a model that is representing the patterns or the phenomena in the built environment or natural environment, and also the social systems, and also understanding what is the location attribute of that. That's why we consider the spatial dimension of that. And also we need to make scenarios to address the model-based anything. So we need to run the scenarios to understand what are the implications of our decisions and make a decision. And then after that is about the visualization and communication. It can be in an immersive environment, it can be in diagram form, but certainly it should be in a digital form where anytime you change the data, you change the scenario, you should be able to see the impact immediately right after you change your model or scenario. So with that, certainly our position is very clear. But what is the role of GeoAI in this urban digital twin? So I believe that Kostas provided the information and the definition of GeoAI, but this is what we actually get from the recent publication of the GeoAI, where the GeoAI is referring to the integration of geospatial studies and AI machine or deep learning. And also knowledge graph is one of the important aspects that should be integrated into that. And knowledge graph certainly is where different disciplines, different capabilities need really to be part of the conversation. And this is a very fast and emerging domain where it's really supporting the data-driven aspects of the digital twin. That's why GeoAI is very important, and it really supports the data-driven dimension, and also increases the frequency and fidelity. So certainly GeoAI as an enabler plays a very important role in all 3 dimensions of urban digital twin: in the data side, the model side, and also the visualization. So a very simple explanation of what does GeoAI do. So take the example of a telescope. So GeoAI is like a modern day specialized telescope built specifically for earth science. Okay, so instead of just seeing data points like the stars, the GeoAI is trying to integrate the geographical knowledge and high-powered machine learning techniques and so on to perceive the patterns, and also to run reasoning about the locations, different locations, and discover new geographical knowledge, new planets and galaxies in terms of the telescope. So certainly discovery of new dimension, and moving beyond simple the observation to gain a deeper and predictive understanding of our world. So that's why again GeoAI is playing a very important role in the digital twin. So back to the Open Geospatial Consortium, where we work on the standardization of the data and also analytics. In Urban Digital Twin Working Group, there are many new standards where it refers to the 3D city model like CityJSON or CityGML, and also BEAM or industrial foundation classes, we also deal with the moving features like the trains, the trams, and vehicles. We are dealing with the position of moving vehicles, even the airplanes with GeoPose standard, and also the sensor things. And MADI is referring to the underground assets and aspects related to that. So the Geospatial, the Open Geospatial Consortium put together an urban digital twin interoperability pilot to address some of these standards and see what is the role of GeoAI specifically from the image processing. And this work, we had the pleasure of leading the engineering report that you can get the report for free, available to the public. So I will share this with you shortly. So what we have done here is improving the training data model AI, which is another standard in the Open Geospatial Consortium, to add the GeoPose, which is coming with a 6th degree of freedom, and improve the processing of the video feeds or camera imagery. So with that, we deal with the location information through the inertial measurement units, or INS, or other type of units, to extract all the location information as much as possible, and then combine those features with the training data model, as you can see here in this side of the slide. So we need to feed the location accuracy into the training data model to be able to run very clear image processing to be able to address the contents related to the image. So with that, our work could be applied for road network quality, which was adopted by United Nations in Colombia, or even the disaster management. As you can see here, a mobile app loads an image of fallen tree, but the image processing is running immediately with the geotag data, and it shows that there is no real challenge in that road network, so that we can actually make a decision in our disaster management cases. Another dimension of the application of the GeoAI is about the autonomous vehicles, pedestrian behavior, and built environment. So we assume that there is a correlation between the human behavior and the built environment design, and that correlation can really help either the vehicles, driver or driverless vehicles, to improve their performance. So here what we have done is using the deep learning to extract the human behavior in different locations, their behavior, how they walk, are they walking, or they have hesitations, or they are turning. So these are some sort of understanding the behavior aspects, and then combining that with the sidewalk segmentation, so that we can bring those sidewalks into the imagery and run correlation analysis, so that we can understand how much the behavior is attributed based on the environment. Another dimension is, I just skipped this one, is the GeoVision. This GeoVision is using large language models that's helping us to really understand where an image might actually be coming from, and make a guess that this image that is coming without any coordinate system attribution is helping us to understand the location attributes. We consider several dimensions in this type of activity. A, what is the optimum number of data for training the model, and B, what is the machine performance from the computational perspective. And we explore different architectures, large language model architectures, to be able to bring the guests of the no LLM filter with the 8,572 meter to 219, to 315 meter through the filtering and adding the GeoVision or Geospatial AI into that. It means that we are moving towards the very high dimensional guess of the LLM to very more accurate type of gesture of the images or any feature that is coming without any geospatial information. And in concluding remarks, I would like to draw the attention to several aspects in the digital twin, and specifically the applying the geospatial dimension into that. We need to really to reflect the reality of world. Here, as you can see here, we are connecting the sensor networks and all the readings in the for the CO2 emission or PM2.5 emission, and this is a 2D representation, whereas the real world is 3D. So we need to move towards that and to be able to address things related to the disaster, pollution, or disease, and so on. But at the same time, we need to really understand the level of validity and trustworthiness of the data, which is a trade-off between the frequency and the fidelity of these analytics. Another dimension that I really believe that is missing in many of the current socio-technical aspects is the role of human, and bringing that human dimension into our models, our techniques, which is really supporting the sustainability and developing future sustainable goals. And that is bringing the different societies into this, communities into the work, and also bringing the social voice into the collaboration into that. So there are many future worlds here, the Geo AI agents that can help us to really add automation systems into the services we provide, but at the same time we need to pay attention to the human side of it and the validity, and also the role of the experts like yourself, how we can improve these type of services. And at the end, I have a number of Geo AI packages listed here for you, so that I hope you can enjoy using these tools, and more than happy to support you in your journey in the future. And with that, I really thank you for your attention, and I'm looking forward to engaging with you with the questions.
Fantastic. Thank you, Dr. Sabri. All right. So we have 10 minutes here left. I'm going to go ahead and open up the floor to questions. And if I don't see any hands, I have a question to get it started. Was that someone speaking up?
No, there is a question about the slides, and certainly happy to share the slides after this.
Fantastic. Thank you.
Here too. Maybe we can create some PDFs of the slides and put them, attach them to CGIA website.
That would be great.
Mark has his hands up.
All right, Mark.
Thank you. Yes, great presentations all. So I'm the GIS manager in South Florida, down in Miami, just south of you, Dr. Sabri, where we have a digital twin, but is not fully fleshed out, especially in the design that you portray in your presentation. So I'm just putting the word out there. I'm Mark. You're Dr. Sabri. I want to be in touch. I want to start implementing some of your methods and modalities. So I'm looking forward to engaging.
Thank you so much. Thank you. Looking forward to it.
All right. So one question that I had, was in the implementation of Geo AI. Have you seen any examples where, there might be a misstep in implementation that leads to a hallucination? Of course, I know AI is always used as this idea to improve things that are actually humanly impossible to do. But in the work that you've done, have you seen any examples where perhaps it's been misused, that would be important to acknowledge?
If I may, this is more of a problem on the LLM system, the natural language systems, but also it correlates with some of the data coming in. Some of the things that I always make sure I caution people and also, pay attention is what are the AI, what kind of data we're using and how biased those data are, especially when you're developing applications that decision makers and the public are using. We might know, especially when you have socio-demographic or socioeconomic data, oftentimes our data are by definition biased, right? So here in Orange County, we have a few, communities, for example, Hispanic or Asian communities, those are big in Orange County. A lot of our data coming, they might be biased towards those communities. So we have to make sure, and as I said before, the AI is as good as the data we're providing. So we have to be careful what data we are using to train our models, whatever bias they have, we have to correct those. We are all seeing some of that hallucinations and issues from the pre-trained data. So even if we use pre-trained data, we have to make sure, and that's what Soheil was talking about, validation and some of the processes. We have to interject before we publish the data to have a stage of validating and assessing the validity of those data. And of course, there's ethics involved. I think that we have a whole seminar of that. There is a whole area of AI called XAI that talks about transparency, sustainability. So ethics are really critical and important, especially when it involves sensitive groups or vulnerability issues on that, and especially when it involves decision making. And then there's one more layer that involves decision makers, right? So there's a whole science of decision making that says, when you face uncertainty, decision makers tends to do what your predecessor do, right? So, so oftentimes people are really reluctant to take, or they are not very risk. So the whole properties of risk aversion when it comes to new technologies plays a role here. So we have to make sure our decision makers make the right decisions, not based on their preconceived notions, but based on science and evidence based.
So quickly, when we are talking about the hallucination, there is this notion that our model may tell us something that looks like correct, but is not correct. So this is a very simple explanation of hallucination. And we are dealing with this hallucination nowadays too much in our model. I can tell you every model has some level of hallucination. And that's why we need to, what we are trying to do is to do scientific AI rather than AI without any verification or uncertainty quantification. So that is the thing that we are doing in many cases, and certainly AI brings a lot of value into our models, and that's why you see that in the definition of digital twin we have data driven, but we should be careful and still using those old models like Bayesian process or Gaussian process any mathematical model that we can inject into the AI to be able to understand what is the level of error. And that level of error is really helping us to understand to what extent we are dealing with the hallucination.
Thank you. And I see, Jay, do you have a question?
Certainly. First of all, Dr. Alexandridis and Dr. Sabri, thanks for taking the time. I'm Jai Shankar Jayaraman, a GIS consultant working for long for the electric utilities and North American market space. So common question to both of you. Where do you see the GeoLLM model maturity compared to the LLMs that we are so accustomed to, right? Whether it is ChatGPT's model or a Gemini model, how do you see it's catching up? That's one thing. And second is, if at all there's one exists that's reliable, what are they training the data sets against to give to the maturity of your other LLM models? I think I was just curious about that. And by the way, Thomas and Tracy, thanks for coordinating this great session. Thank you.
Thank you. If I start with this, first of all, I believe that GeoLLM is moving forward nowadays, but the level of complexity is high. It's exactly similar to the statistics and geostatistics. So we have statistics, which is numerical. We use the numbers, and we can tell that random numbers or random distribution among the numbers. But geostatistics, we are dealing with those numbers plus X and Y at least connected to that, so that we can actually make things really heavy. And GeoLLM is exactly the same thing. And also in the diagram that Kostas demonstrated, the reasoning, spatial reasoning, spatial, perception, all those dimensions are adding when it comes to the GeoLLM. It certainly is moving forward, but is from my perspective, is scratching the surface. So it needs really pay attention, and rather than moving fast forward, certainly we need to test the applications and consider 3 dimensions into that: semantics, topology, and geometry. So we have been using this for building level, for the building approval, for example, using LLM for building approval and so on. But these 3 in every applications, like yours, in your case, which is the engineering and aspects, these semantics, geometry and topology are very important to test and understand how the LLM is performing. And in terms of the data set for training, in the GeoVision case that I demonstrated to you, we had a case in San Francisco where millions of data, image data across the city were used for GeoVision analysis, and we are trying to come up with an optimized level, and that optimized level again needs some sort of mathematical understanding of how we can pick less number of images to analyze, to be able to train the data, but the coverage is in a way that is representing the area. And that optimization, again, it comes into place, and we need to always to pay attention to what is the level of optimization, how we can use models like Monte Carlo or models, again, old models, which are very significantly important to be used to optimize the model and increase the level of accuracy in the training data, so that then we can have some sort of confidence for the training of the subset of data on that.
And if I might add to that in a more technical level, I think apart from the descriptive metadata and the description of the GIS data and the maps and all those things, we need LLMs that train into object-oriented geographic or geometric data. And that perhaps that means that we need to train our LLMs into GeoJSON data formats to be able to recognize objects and relationships. We are not there yet, but I think there needs to be a coordinated effort, both from the academia and the expert side, but also from the industry, like Esri and other geospatial consortium, to start creating models that train from, for example, GeoJSON or GeoSQL servers or things like that that understands relationship in space and geometries.
All right. Well, thank you both. We are now about 2 minutes past. I saw there was someone who raised their hand to ask a question, but I wanted to ask, would you be willing to answer it? If not, that's okay. Okay.
I think it was Nick Frantino.
Yes.
If we're out of time, I can just throw it in the chat.
No, go ahead.
Yeah, go ahead.
Okay, great. So you guys mentioned that Esri geodatabases might not be so good for AI agents. So does that mean the best practice would be to get the data out of silos, would be to share online, like ArcGIS Online, open data resources, data hubs, and REST services? So if that is a best practice, can you talk about the importance of metadata in these tools as well?
Right. I think this is really, really critical. That's where the standardization comes in. Remember, I talked about, those type of models require higher standardization and so yes. So getting the data out or maybe training the models from GeoJSON or REST endpoints and things like that might be a feasible way. I haven't tested it yet, but I can see how it can be done. But in order to do that, we all have to start getting into the practice to populate really advanced and really detailed metadata. Because if that metadata doesn't make it to the REST endpoint, there's no way to understand what the system does, how the relationship are formed, so those practices. So we have to develop maybe standards and protocols, not only publishing data, but publishing data with advanced metadata that they are ready for GeoAI.
Thank you.
All right. That's all. Before we end here, I wanted to thank our sponsors. Oh, did I stop sharing?
Sorry. Let me ask some of the participants if you have any more questions for me or Soheil. I think Thomas shared our GitHub, our LinkedIn profiles. Feel free to send us a note and ask us. We'll be happy to reply.
All right. Yeah. So we want to thank our sustaining members for the CGIA. That's California Tribal GIS, Dewberry, Parcel Quest, Quartic Solutions, Redefined Horizons, Shasta College's GIS program, UC Santa Barbara's Geography program, USA North 811, Dig Alert, and USC's Dornsif, the Spatial Sciences Institute. Thank you for your support and for making this event possible. Without further ado, Dr. Alexandridis, Dr. Sabri, thank you for your time today to share with us your knowledge and your information. I certainly learned a lot, and I can see that I'm going to be learning a lot more through the course of the series. So thank you all for attending. If you have any suggestions or comments for us on how we could run these sessions in the future or have any ideas for future events, please reach out to Tracy at chair@cgia.org and check out our website to learn about more upcoming events. All right. Thank you all. Have a good rest of your day.
Thank you.
Thanks, everyone. Great job.
Thank you.
Everybody.